Good morning and welcome back to Nuclear Everyday.
On today's episode, we are going to talk about what nuclear physics, accelerators, and paintings all have in common.
Around the world, particle accelerators are being used for ion beam analysis, or IBA for short, helping scientists explore everything from new materials for satellites to ancient artifacts and more.
However, we will be focusing on one of its more unexpected uses, analyzing artwork without ever touching the surface.
Here at National Institute for Physics and Nuclear Engineering, Holea at the 3MV Tendentron, there is a beamline specifically made for ion beam analysis.
Light ions are accelerated by the electric fields inside the tendentron and then guided by magnets to the right beamline. At the end, the beam intersects with the target, and information is gathered based on how the material's atoms interact with the incoming ions. That is IBA. But what makes it special?
Well, first of all, it's non-destructive, leaving the target intact. You can also analyze different thin layers in the target, identify a wide range of elements, and works in atmospheric conditions. It includes techniques such as particle-induced X-ray emission, particle-induced gamma-ray emission, and Rutherford backscattering spectrometry.
In particle-induced X-ray emission, a high-energy proton hits an atom and knocks out an inertial electron, which is then replaced by another electron, emitting an X-ray specific for each element. In particle-induced gamma-ray emission, a proton strikes the nucleus, exciting it. When it returns to a stable state, it emits a gamma ray characteristic to the element. These techniques complement each other, the former being used for medium to heavy elements at the surface, and the latter for lighter elements.
In Rutherford backscattering spectrometry, the ions elastically collide with the nuclei of the target and scatter back towards the detectors. The energy of these backscattered ions depends on the mass of the nucleus and the depth where the collision happened. As such, RBS is very useful for understanding layers and their order and identifying heavy elements, being particularly sensitive to them.
The old paintings, for example, contain certain type of pigments, right? So if, for example, you identify some titanium oxide in a painting that is supposed to be very old, then maybe it was intervened, it was somehow restored, or maybe it's just a fake. But again, the final answer should be given by an art expert, not by physicists or by chemists.
So next time you're looking at a famous painting, just imagine, science might have verified its authenticity.
And it's all thanks to nuclear science and accelerators.
We hope you have enjoyed this episode of Nuclear Everyday, where we discussed how nuclear physics is used in art analysis.
You can watch the full interview with scientist Mihail on our channel and tune in next time when we'll be discussing how radiation can be used to track pollution across continents.
We'll see you next time.